This is FE Peer Review. The date is February the 20th, 2022. Brian's Logic asks, how big can the globe Earth get? This may be old news for some of you. Brian put this video up a month ago, January 18th. I don't make a habit of checking on the channels of flat earthers, but YouTube, in its wisdom, decided to throw this up on my list of videos to look at. You know, there it goes, still promoting flat earth channels. So I glanced at it, and I'm going to play it for you. It's just under a minute long. I'll play most of it, not all of it. I left him a comment, and this video is pretty much my comment, but I'm going to add a few little bits to it. Lots of good responses to his video from all the familiar names. Encourage you to go and check it out. Now we'll watch his video.
Well, how are you doing? There's another quick video. Another question for the ballers. For all the ball legends out there, this is obviously the diagram of the Al-Biruni method for determining the radius for your globe. Now, we all know that's a load of rubbish, as it's been proven to be totally debunked. So this is my question for our globe friends. Please answer this question, ball believers. Can the globe Earth model be bigger than we are told, which would mean that its claimed radius value could change, be bigger than 3959 miles as an average, let's just say, right? Just doing that. Miles as an average. And if so, how big could it be? So, how big can your globe be? Thank you.
Okay, so here's the first thing I have to say. Now we all know that's a load of rubbish, as it's been proven to be totally wrong. That was a quote. This is a typically ambiguous statement, typical of a mind that is unclear in its thought processes. What's wrong? His technique or his final result? His approach to measuring? His approach to calculating based on the measurements? And or the final result he achieved? So no, we don't, quote, all know. Please clear that up. What are you saying Al-Biruni got wrong? By the way, Al-Biruni measured in cubits, and there are many different historical measurements of cubit. It was not standardized as measures such as the meter or foot are today, so we don't know the precise radius he actually obtained. We do know that he was not aware of atmospheric refraction, and so would probably have overestimated, but we don't know by how much, since we don't know the degree of refraction present on the day of his measurement. However, some of the cubit conversions would put him within just a few percent of Earth's actual size. Regarding measurements and right or wrong, suppose you're going to measure two objects. You have a tape measure whose smaller increment shows as 1 millimeter. You measure an object with it and read a measurement of 10 millimeters. But in actuality, when measured with something much more precise like a caliper, it measures 9.8 millimeters. Your first measurement varied from the object's actual size by 2%. Does that mean your 10 millimeter measurement is, quote, totally wrong? What if you use your tape measure to measure something and you read that it is 10 meters long, and then check it with more accurate measuring device and find it measures 9.8 meters? Is your 10-meter measurement totally wrong? After all, it varies by 200 millimeters from the object's actual size. On the other hand, it is only 2% off, like your earlier measurement of the smaller object. So is your 10-meter measurement totally wrong? You asked, can Earth be bigger? I suppose, in theory, yes. It isn't, but I suppose it possibly could be. There's a lot of complicated physics relationships to consider.
This is obviously the diagram of the Al-Biruni method for determining the radius for your globe. Now, we all know that's a load of rubbish, as it's been proven to be totally debunked.
Obviously, we all know, if you can do it, so can I. There are much bigger and more massive planets out there. So planets can be bigger, and we could have underestimated the size of ours, but we haven't under or overestimated ours. Using the best measurement tools we've got, something better than your standard tape measure, we are way better than 2%. Like, we're talking about meters of accuracy over the entire Earth. In fact, I think I read just a few weeks ago that they did some new calculations based on additional measurement data, and they have officially moved the location of Earth's center of mass to a new spot, 2 centimeters away from the old spot. That's less than an inch. So, no, we didn't get it wrong. We have it. In this little BBC documentary, they kind of recreate the approach that Al-Biruni used, including the tools he had to work with. I'm just going to let it run in the background here while I talk. I've got the volume off. So, Brian, there's his astrolabe, and he's got an assistant there to hold it while he adjusts the arm on it. And it was with tools as simple as that he was able to make his measurements. I mean, and this was, I forgot the year, this was many hundreds of years ago. And I mean, even if he was 20% off, I think it's pretty amazing to be able to accomplish that with such basic tools. And my hunch is he's probably much closer to 2% than 20%. I'm sure he did a really meticulous job. As the guy says in the video here, he here in the video is not being anywhere near as careful as Al-Biruni would have been. So, Brian, can you measure the Earth, whatever shape it is, as accurately using such basic tools as this? Other people have. I'd love to see you go about it. Give it a try. That would show some real conviction to support your ideas that you propose about things. Will you be doing that, Brian? I did it. Lots of us have done it. When I was an engineering student almost 40 years back, I measured it. Well, I did with my classmates. I took 2 semesters of surveying, and we did what's called the reciprocal zenith measurement. I think if I remember right, it was a team of 3 of us, me and 2 other people. And we had set up 2 stations 1,000 feet apart and took all the measurements and did all our calculations. And we got to within, I don't remember, it's been a long time, 1%, or less than 1% of figuring out Earth's radius based on the simple procedure of a reciprocal zenith angle measurement. Now, we did this before GPS and all of this digital stuff was available to the public. The U.S. military had access to it, but they had not yet opened it up to anyone outside the military. So all of our equipment was totally analog, and yet we were able to accomplish this. I think it'd be great. This was at a community college. I started at a community college, and there's probably some kind of an equivalent community college system where you live, Brian. You could probably go and for very little money, maybe even free, take a surveying class and get a chance to use these tools, try them out in the field with a teacher who knows how they work. It'd be fantastic training, and I found it a lot of fun. I mean, I was tempted to just stick with surveying. I ended up going into engineering, structural engineering, but I really enjoyed the surveying stuff. So that's something you might want to think about, Brian. Get out there and get your hands on the tools, take a class, get a teacher who can show you how to use the tools so you don't waste a lot of time just learning the equipment, and hook up with some other students, other people that are interested in the same thing, and go measure stuff. It's quite fun. Al-Biruni did it. I did it. Lots of people have done it. You can do it too if you're interested. So, no, we didn't get it wrong. We haven't over or underestimated it. Now, could it theoretically have been a different size? That I'm not sure. Possibly. There's physics involved that I simply don't know, though. Here's what I mean. I understand that Earth is primarily composed of iron. Assuming we have a given fixed amount of iron atoms floating in space in a cluster near enough to exert gravitational attraction on each other, those atoms will gradually coalesce into a sphere. My gut feeling, but as I said, this is beyond my current knowledge base, is that this iron will find equilibrium at some specific density. In effect, for a given amount of iron, it will coalesce into a sphere of a specific size. We would not get, for example, a planet identical to Earth's atomic composition and total mass, but coalesced into a much smaller or much larger sphere. It would coalesce into a sphere of the same density as Earth, and having the same mass, it would in consequence have the same volume and radius. What is your question leading to? Are you thinking about how atmospheric refraction might have affected Al-Biruni's measurements? I'll touch on a couple more points that were beyond my original comment. If you look up Al-Biruni in Wikipedia and it describes his observation, it's my understanding from what I read here that if you indeed apply a refraction correction to his observation, assuming standard atmospheric conditions, and if you pick a conversion for the qubit that's somewhere in the mid-range, most likely range of what he would have been using given his time and place, he was within 2%, or he might have been within 2% of the correct value of Earth. On the other hand, if you factor out the refraction correction, if you don't include that and you look at some of the other qubit conversions, he might have been off by as much as 20%. We simply don't know. I think Brian could afford to take a little time to look into what's considered accurate as far as measuring. It varies from scientific discipline to scientific discipline, from purpose to purpose. I just glanced around online quickly to see what I could come up with, and I came across this document from the California Department of Transportation. It's Caltrans, and it's part of their kind of like specification to contractors as to what degree of accuracy they expect from geodetic surveys. There's an example. So you'll find accuracy criteria listed there for that specific purpose from that specific organization. You know, these things are worth understanding. Is something totally wrong because it's 0.002% off? Might be if you're, I don't know, trying to do particle physics experiments at CERN. On the other hand, you'll be lucky to get it less than 2% off if you're building a highway out in the middle of the desert, right? So what is accuracy, Brian? That's a question I have for you. What is accuracy in measurement? What does that phrase mean to you? And how does it apply to our attempts to measure Earth's shape? I finished the video, but I decided I need to add one little addendum, so I'm going to tuck this little bit in here. Going back to Brian's original post, he's got this image here, but the title of his video says, "How big can the globe Earth get?" I'll now answer that question to the best of my knowledge. No bigger than it is. If we ignore things like bits of dust coming through the atmosphere or the debris of meteor strikes, basically, it's as big as it is, and it's not going to get any bigger. Now, if you meant to ask, Brian, how big can the globe Earth appear to get, based on observations which are influenced by effects like atmospheric refraction, I've got a different answer. And that is very, very much bigger. In fact, you can have refraction to the point where it appears flat, which is effectively an infinite radius. And you can go beyond that on rare occasions to have atmospheric refraction that makes it appear concave. So, to answer your question as you actually wrote it, no bigger than it is. To answer another question which you might have had in mind when you wrote your title, the answer is infinite. But what it appears to be is entirely a separate question from what it is. All right, that's it. End of addendum. All right, I think I have to go. Trying to keep this to under an hour's work here. Things are going smoothly in my world. I'm making lots of progress. I'm still here at home for a couple more weeks. No, not yet. One more week. Then I'll be running around, so it'll be harder still to do work, but I'm going to do what I can. And I hope you enjoyed this. Remember, there's a like button down there, and of course, room for lots of comments. So have a great day, everybody. Bye-bye.